Okay, so we are finally connected here. Today is going to begin the material for exam number 3. And on exam number 3, if you look on your syllabus, we're going to have muscle, mostly skeletal muscle, a little bit of cardiac muscle. We're going to have cardiovascular, heart, and we're going to have blood. But because we're doing a blood lab tonight and Thursday this week, I'm going to start with blood. Okay, and the blood will take about an hour. It's not a very long chapter, and then we'll take a little break, and then we'll start with muscle today. We will get started with muscle, and we'll finish up muscle on Thursday. That'll put us in good shape to have a good 2 presentations on heart. When is exam number 3? Is it a Tuesday or a Thursday?
Thursday.
So I actually have 3 more spots, don't I? So there's no test next week. No lab exam and no lecture exam. This is like a moment, so remember it. So next week, we'll finish up muscle, I suspect, this week, and then that'll give us next Tuesday, next Thursday, and the following Tuesday to hit the heart, which is really important. And we'll be talking about blood pressure and the heart and cardiac output and lots of good stuff about the heart. And there might be a little bit of time even at the end of that for a little review session, sort of like I did last time. If I get ahead a little bit, I'll try to give you a time for questions and answers. And then that exam will be a week from this Thursday. It's only 10 days away, but it seems like a long ways, right, when we've been working so hard this semester. No, not 10 days. More than 10 days, right?
Yeah.
Like a lot of days. Okay,
Yeah.
a lot of days. Okay, now, I've also been putting off discussing the case studies because I didn't want to get behind, and now's a good time to do that. So let me introduce you to the case studies, and to do this, everything you need for the case studies is going to be on Blackboard. Go up under lecture materials, and one of the links is going to say case studies. Now, I've had this open for a while, and what you're going to see is this. At the very top, it is instructions on how to upload your answers. So once your group is done, you'll click on that, and you will upload your responses to the case study on SafeAssign. I think most of you have done SafeAssign before, and that's going to be a place for anti-plagiarism to make sure that you're not copying from a group in the previous semester or year. Then what you'll find is that down here I've put together a collection of case studies. There's group 1, and all of the group 1 case studies have something to do with the scientific method or with musculoskeletal physiology, kind of what we've been dealing with or about to deal with. Everything in case number 2, or group number 2, deals with either neuroscience or endocrinology. So those are all topics we've either talked about or are about to jump into when it comes to the muscle phys. Each group will choose 1 case study from group 1 and 1 case study from group 2. Your choice, okay? So what you can do is just kind of click on them. If you click on these links, it will bring you to the title of it. And you could just take a quick look and say, you know what, am I interested in MMR vaccines and autism? If so, choose that one. You can look through it. All of these case studies are put together by the University of Buffalo, and they all sort of run the same idea. There'll be a little story. At the end of the little story, there will be some questions. Okay, so here's a couple of questions here. And down here, here's a question for part 3. So there really aren't that many questions. Here's a graph and a couple of questions about that. So I think there's a total of 5 questions for this entire case study. This is not an overwhelming amount of work. For the case studies, though, you're going to type up your answers to them and cite anything that you looked up, right? So we know how to do that. So if you look up something out of some journal or some book, always cite your sources. So as long as the groups will do the answers to the best of your ability and then cite your sources, you should expect to get the full credit, which is 25 points per person for these case studies. You'll turn them in. I need a hard copy of the responses and an uplink, okay, to SafeAssign. So both hard copy and uplink. For the groups, I would like to see groups of 3 or 4 do these. Now that is for most of you, your lab group. Okay, most of the lab groups are 3 or 4 students, and so that is just a natural place. You're hanging with them once a week. You've gotten to know them, doing your lab physiology report, and they're just a natural group of people you've already worked with. But if you don't want to work with them, you can switch around. That's okay. But I don't want any lone rangers. Okay, please do them in hopefully groups of 3 or 4. If there's a group of 2 that absolutely insists on it, I'll think about it. But please, I'd rather put 2 groups of 2 together in a group of 4 just to reduce your workload. I mean, there's no reason to work more for the same number of points. Now, at the top of this list, it says there's a case study group report form. This is just a little form that you will attach to your responses that basically says, here were the members of my group, and we did equal effort, and you sign the form. Okay? And the point is this: I don't want to find out after somebody turns it in that Susie did nothing, right? Susie put her name on the form, and Susie did nothing. Well, if Susie did nothing, she's got to sign this thing and say I did nothing, right? And I will make some adjustments on grades based upon that. But every person who's submitting a part of a case study must sign this form as part of the group. And I really have not had issues with this. You guys can decide what equal effort is. So maybe some of you are more about looking up and researching. Some of you would rather type it up, whatever, right? You kind of divide up the work amongst yourselves, sign it, and I must have this form attached to it with all signatures before I will grade it. Now, the assignment right now is due when? Case study number 1 on the syllabus says that it's due next Thursday. I want to give you till after exam 3. Why don't I give you until there's a second one? So let's not go too late. Let's say Thursday, July 16th. On your syllabus, it says that's the day that case study 2 will be assigned. Okay, that gives you what, an extra 2 weeks or so? Okay, I think that's reasonable. I will take them anytime. Okay, you can give them to me as soon as you want to, but that'll be the due date. And then there will be a second set of these case studies that will open up about that time and will be due the last week of classes. No matter what the syllabus is, I'll just push it back a little bit as well. But again, every group will choose one from group 1 and one from group 2. Okay? And then when we get to case studies number 2, just so you know, those topics will be about cardiovascular and blood respiratory, and also about immunology, urinary, and reproductive. So we'll have case studies somehow linked to the content that we're discussing as a class. If you have any questions, just drop me an email or talk to me in lab about this. The only reason that people don't get full credit for this, honestly, is not citing their stuff. So just make sure you have citations. Okay. A lot of these questions are, you may do a little bit of research, just a little bit of research, and you'll learn some things as you're doing it as well. Any thoughts on the case studies? Okay. Let's then move on, or back, I should say, and let's go back to blood. And I've got on here for you to review a couple of modules, and these are the real basic things. Now, in 105, what I recall is that when we talked about blood, we talked mostly about red blood cells. We really didn't talk a whole lot about white blood cells at all. They were there, right? And there were 2 groups, granulocytes and agranulocytes. And in lab tonight or on Thursday, we'll dive in a little bit deeper. And what I'm talking about now will complement what you did or will do in lab nicely. And I think that's all the prelude I have to say. Any questions at this point about exam number 3, timing, anything at all? Okay, let's jump into blood. So this is chapter 17 in your Martini book. Some of this is pretty obvious. Blood, we know, is a connective tissue, right? Don't ever forget that. It's a bunch of loosely packed cells with ground substance, and we know that this blood is going to be pumped by the heart and is going to help maintain blood pressure, right? The fluid levels and the blood cells are going to help maintain the volume of the blood. And we know that there's a series of tubes that carry this blood, the blood vessels, arteries, always away from the heart, veins always coming back toward the heart, and capillaries, the connector between those where diffusion not only of oxygen occurs, but also where CO2 and nutrients and hormones are oftentimes exchanged. Blood is carrying everything, right, through your plasma. So when you think about blood, you think about the water that's in there, but there's also nutrients and hormones and waste products and a number of other proteins as well. That blood is helping to regulate our body temperature as it distributes heat through our body. And don't forget that in addition to delivering oxygen by red blood cells, it is also delivering white blood cells, which are very important in fighting off infection. It doesn't matter if it's a virus, a bacterium, a parasite. There's going to be a certain part of the immune system and your white blood cells that are dedicated to fighting that off. So again, this was that chapter I said kind of review on your own. We get the idea, right? No problem with vessels. We know that arteries are usually red, right? Veins are usually blue, the exception being the pulmonary circuit. And I'll remind you of that when we get to the heart. So I've already said this, right? That the blood is transporting things. It's transporting gases, nutrients, oxygen, hormones, all of your waste products. All of that is being carried by your blood. And some of the physiology here. Remember, what is the pH of your blood? 7.4, right? That's one of those numbers you just kind of keep in your head. And that pH of the blood is very important. And we'll be talking about quite a bit of our discussion, actually, at the end of the course. We'll deal with both how the respiratory system and the urinary system are battling constantly to keep your blood pH at 7.4. It's an incredibly important homeostatic norm. And if it varies too far off that norm, we've got some very serious trouble. So we're going to see how the respiratory system and blowing off CO2, and we're going to see how the urinary system getting rid of acids is going to be very, very key to helping keep that pH stable. Also, the ion composition, right, is very important. And we've begun to understand that. We now understand the critical nature of sodium and potassium and calcium. We've seen how important those concentrations are for action potentials, and we'll see again how important they are for muscle contractions, and we'll see in this chapter also how important calcium is for blood clotting. So we know that keeping those calcium and ion electrolyte concentrations stable is also very, very important. Things that are moving in and out of blood are primarily moving through diffusion. Remember, diffusion is moving from higher to lower concentration. Most of the stuff is moving at the capillaries, right? Remember, the capillaries have one layer of cells, right? Capillaries are just a simple squamous epithelium. And remember that some of your capillaries also have fenestrated capillaries, which means that they have windows or openings, some bigger gaps in those capillaries for diffusion of larger molecules. Blood is also going to help with clotting if you should have an injury, in which case you're losing blood. The blood will clot, and we'll go through those scenarios. Toxins and pathogens, again, I've already mentioned this. White blood cells are designed specifically to fight off certain pathogens. And as blood is traveling through, it's helping to stabilize your body temperature. Little chart reminding you of all those good things. So that was 17.1. 17.2 was what is found in blood. Again, this is mostly review. Remember that blood is composed of the plasma, that's the watery portion, the ground substance, as well as the formed elements. The formed elements include the cells and the cell fragments. Another way of saying that, it includes the red cells, the white cells, and the platelets. Right? So the red cells, the white cells, and the platelets all make up the formed elements. And in an average male, somewhere between 5 and 6 liters of blood. Between women, between 4 and 5 liters of blood. The difference just based upon body size. Okay? That's not composition, that's simply volume. Okay? So a smaller man or a taller woman, again, those are just averages. Now, whole blood, if I were to bleed your arm, right, that would be whole blood, and we would find that the temperature is about 1 degree warmer than your body temperature. So about 100 degrees Fahrenheit, 38 degrees Celsius. And we know that blood is thicker than water. We got that. It's more viscous than water. And that viscosity, that thickness, is due to the proteins that are mixed in your blood. They kind of stick to each other and make it a thicker solution. And we know that it's slightly alkaline. We've already said we know the average is 7.4. You want a normal range of 735 to 745. So there's not a whole lot of wiggle room, right? 735 to 745 is, the normal range for blood pH. In lab tonight and today, we're going to be fractionating or separating out the blood. And what you'll see is that In lab, we've got horse, goat, and sheep blood, rather than blood of my students. And we'll be separating the blood out. Now, in your blood, my blood, the plasma would be about 55%. That means that everything else is 45%, that everything else would be the formed elements. So the formed elements, the red, the white, and the platelets, would all be the 45%. Now, of the formed elements, we'll measure this called a hematocrit. A hematocrit is basically a small centrifuge tube. We'll take the blood and we'll spin it, and all the red blood cells will pack down to the bottom. So you may also see this called packed cell volume, PCV. But hematocrit, I think, is more common. When you spin the blood down and you have the red blood cells at the bottom, that percentage, or sorry, what did I say? What goes to the bottom will be mostly red blood cells, and that 99% of your formed elements are red blood cells. Let me repeat that. So 99% of your formed elements are red blood cells. Only 1% are the white blood cells and the platelets collectively. Overall, about 45% hematocrit. Males, averaging around 47. Those who just came out of lab, is that the average I gave you for males? Maybe 48. Okay, so you're going to see different numbers. So don't call me up and say, Mac, I've got different normals. It's going to be, even if you talk to people in Denver, because in Denver, they're at a higher altitude. Their normal hematocrit will be different than those at sea level. So you're going to see a few different standard numbers, 47, 48. We're still roughing around high 40s, right, for male average hematocrit, and for females, 42 average. And I think the lab manual said instead 40. Did it say 42? What do you know? Hey, when it's the same, it's even better, right? So somewhere in the low 40s is average for women. So again, I'm not going to be asking you which is exactly the average. Just know that ballpark. The difference has to do a lot with testosterone, which is much higher in males, of course, and testosterone does drive up red blood cell production. Do you remember what hormone? We'll get to it in a few minutes. But what hormone drives up red blood cell production? I'll mention it now. Erythropoietin, EPO, right? And I'll spell it out. Oops. Erythropoietin. Can you even read that? It's horrible. There we go. Erythropoietin, right? Or poietin. EPO. And that hormone is kicked up by testosterone, and that hormone is made largely by the kidneys and travels to the bone marrow and upregulates the production of red blood cells. So in lab, we'll be doing this. We'll be looking at a hematocrit. Again, this should be familiar and comfortable. If I took whole blood, or a tube of whole blood, that would consist of plasma and formed elements. If I spin it out, then I'll see what happens here in a moment. But the plasma is made up of proteins, about 7% proteins. We'll go through who those proteins are. We've seen that before. And about 92% water. Right? So your plasma is about 92% water, mostly water. And then the formed elements, of course, 99.9%. I mean, the vast majority of your formed elements are red blood cells, white cells, and platelets, making up just a small fraction of the rest. So let's talk about what's in blood. In the plasma, water, right? 92% water, about 7% protein. Those proteins, will go through those proteins, and then 1% is everything else. The ions, the hormones, everything else is traveling through there. The primary difference between plasma and your interstitial fluid. What's another word for interstitial fluid? Extracellular fluid, right? So the stuff outside of cells. Really the only difference between plasma in your blood vessels and interstitial fluid outside of your blood vessels is the concentration of gases. Right? What I tell you drives the movement of oxygen, or most things, in and out of your capillaries. Diffusion. And we know that diffusion is driven by a concentration gradient. So there has to be a difference in concentration for oxygen to travel from interstitium into blood vessels and vice versa for CO2. The other thing is your proteins in the blood are too big, right? So in normal people, the albumins and the other proteins that are dissolved in your blood are simply too big to get across the blood vessel. So really the big difference is concentration of gases, CO2 and O2. The electrolytes, the proteins are essentially the same on both sides. So these proteins are different than other connective tissues. When you dream about cartilage and bone and fat, the proteins that are dissolved in those tissues are insoluble, right? They're part of the tissue. They're out of solution. But in blood, the proteins are in solution. They are soluble, right? They're dissolved in the plasma. And again, about 7% protein in the blood. That's quite a bit. I mean, that's 7 grams of protein in 100 milliliters of blood. That's a lot of stuff that's dissolved in there. And again, the size of the proteins prevents them from getting out of the capillaries. 90% or more of your plasma proteins are made in the liver. So as I go through these proteins like albumin, when I go through and talk about fibrinogen, and these proteins are largely made in the liver. One of the clinical signs of a person with liver failure is ascites, a buildup of fluid. And we'll get to this in a moment, but they get a big buildup of fluid in their body. Why? Let's go there now. Why not? Why would a person with liver failure accumulate fluid in their gut? The liver is making blood proteins. Proteins, aka solutes, suck. If you're not making enough blood proteins, then water is not being drawn into and kept in the blood vessels. So water now stays outside of the blood vessels in the interstitial fluid of the body. And so without good liver function, people have ascites. That's just the name for this fluid buildup that occurs usually in the gut, right, around the liver itself. But you'll see a big belly. And that's the same thing that happens when you see children in developing countries, right? They've got a low protein diet, but they've got little skinny arms and big bellies. It's the same thing. They have ascites as well. Because they don't have enough protein in their diet, they don't have enough protein in their body to make these albumins and these other proteins. And so it looks like they have these big fat bellies. It's just fluid. So here are the proteins that are made in the blood. Number one, albumins. By far the most abundant, albumin abundant. About 60% of all the plasma proteins are albumins. This is really egg white. It's the same protein, right? It's a very abundant protein. You could, put it in a frying pan. And this is the major protein that's going to help maintain your blood pressure. That plasma oncotic pressure is a fancy way of saying the proteins that keep the fluid in your blood and keep the balance of fluid. The second group of proteins in your blood are the globulins. You may know them better as your immunoglobulins. These are your antibodies, right? These are the antibodies that are helping you with your immune system. And there are other globulins that help transport proteins. And do you remember one of them? When you hear the word globulin, and I say carrying thyroid binding globulin, do you remember maybe just seeing that word? So some of these globulins are also not antibodies, but instead are helping to transport molecules like the thyroid hormone through the blood. And then the third most abundant, really kind of small, 4% or so, is fibrinogen. Fibrinogen is a soluble, right, dissolved protein in the blood, but when anything happens to the blood vessels, damage, then there's an enzyme released that causes the fibrinogen to be cleaved to fibrin. It's actually the fibrin that forms the blood clot. So those are the big ones, right? We got albumin, the globulins, and fibrinogen. There's also a bunch of plasma electrolytes. Think the sodium, the potassium, and the calcium that you know about. The other electrolytes on here are the same ones you see in your vitamin bottle. So magnesium, chloride, bicarb, phosphates, sulfates. Those are things that are either important molecules in your biochemistry. There's also some organic nutrients, right? These would be what? Organic meaning molecules that have what in them? Carbon. So we're thinking about lipids, carbs, and proteins, right? So there are molecules floating through your blood, and those molecules are going to be used for energy and making of ATP. And then there are also going to be organic wastes. We'll be dealing with this a lot when we get to the urinary system. On the bottom it says urea and uric acid. Those are organic waste products that are made by the body as a waste product of metabolism. So as your body takes in energy and makes proteins and makes lipids, it makes these waste products. The problem is these waste products are mostly acidic. And those acids would accumulate if the kidneys were not constantly getting rid of these acids. Now, if the kidneys aren't working, right, so we talked about liver a little bit, right? What happens? The liver's not working well, you don't have enough albumin, you get ascites. What about the kidneys? If you're not getting rid of these waste products, then the pH of your blood would begin to drop, right? You become more acidic, pH would drop, and we would say that you have what condition? Acidosis, right? So you're accumulating acid. These acids are a normal product. You are making acids all the time, and the kidneys must get rid of this acid. So again, we're going to be spending a lot of time in the second half of this course talking about how the kidneys make sure this doesn't happen. Okay, so that's the plasma, that is the proteins. Now let's talk about the formed elements, platelets, right? Little tiny fragments of cells, very small percentage, about 0.1% of all the formed elements. And they are actually little fragments involved with blood clotting. It doesn't say it on here, I'll go ahead and say it now. These platelets are made by cells called megakaryocytes. And those megakaryocytes are in the bone marrow. So these cells are in the bone marrow. Of course, all of your formed elements, right, are made by the bone marrow. That's the platelets, that's the red cells, and the white cells. They're all starting their journey in the bone marrow. Then there are the white blood cells. We'll get to know a lot more about them. They are also relatively rare, accounting for less than 0.1% of all the formed elements. Remember, red blood cells are 99.9 or so percent. So they are the big player as far as raw numbers go. They're all involved with your body immune defenses, and we'll be learning about them in lab. Red blood cells, your erythrocytes, you guys know these, by far the most abundant, essential for oxygen transport. That's what these cells do, right? That's their job. Their job is to transport oxygen. They also transport some CO2. And what's the molecule that carries the oxygen? Hemoglobin, right? And so red blood cells are, by their very nature, red because of the hemoglobin. So the hemoglobin molecule is what makes them red without any staining. It's just a natural occurrence. So just a picture of all this. If I took all of your formed elements, which would account for about 45% of everyone in the room, for gals fewer, for guys more. Here are just the breakdowns, right? Less than 1%, just a nice picture. 99.9% or 99 or better for your red blood cells, and then little pictures of these. And this is what we're going to be focusing on in lab this week. We're going to be taking a look at these white blood cells and learning how to recognize them, learning about what their purpose is in our body. So that was all review, I hope, mostly review. Okay, so let's talk about how these formed elements are produced. I just mentioned that all of your formed elements, red cells, white cells, and platelets, are all made in the bone marrow. The process here is called hemopoiesis. You may also see the term hematopoiesis. It's the same thing. Okay, just a choice of words. So hemo or hematopoiesis, the making of blood. And there are cells called hematopoietic stem cells. These cells are sitting in your bone marrow, and their job is to continuously make new formed elements. Your body is constantly making platelets, your body is always making red blood cells, and your body's also making white blood cells, although it's not making white blood cells as many because white blood cells are true cells. Because white blood cells are true cells, what can they do? They have a nucleus. They can divide. So they can make more of themselves, but platelets and red blood cells are a dead end. They have to be constantly made from scratch. There's no way for these to divide. So the cells that are in charge of this are the hemocytoblasts or the hemopoietic stem cells. Same thing. They're self-renewing. That's the definition of a stem cell, right? Stem cells are cells that just kind of keep on going, keep on going, keep on going. They're multipotent. That is a term meaning that one cell can become multiple cell types. So the same cell can become a red blood cell. The same cell can become a white blood cell. The same cell can become a megakaryocyte that makes platelets. That's what's meant by multipotent. So these cells have the ability to differentiate and become anything they need to be within the blood cell. And we're going to see that there's two main groups of these cells. Now, these hemocytoblasts, right, it's the same thing as that hemopoietic stem cell. These hemocytoblasts basically have a big old fork in the road. So when they begin to divide, they have a big old fork in the road. They either become lymphoid stem cells or they become myeloid stem cells. This is really easy. The lymphoid stem cells are the stem cells that become lymphocytes, and that's all they become. So the lymphoid stem cells only become lymphocytes. Easy, easy, easy. Now those cells start in the bone marrow, right? But most of them migrate. They leave kind of early, and we'll talk a little bit more about this when we get to the lymphatic system, because this is where the blood and the lymphatic system start talking to each other, because these are the cells, right, that are part of your lymphatic system, your immune responses. And some of these cells are going to go to your primary lymphoid tissues, such as your spleen, such as the tonsils, the thymus, the lymph nodes. So these cells are going to be hanging out. They're going to go to certain places in your body to help protect you. And then there are the myeloid stem cells, and they can become everything else. So myeloid multiple, myeloid many. But the lymphoid only become lymphocytes. The myeloid can become all of the other cells. So that would include erythrocytes, all of the white blood cells, except lymphocytes, and platelets. So just a visual on this. So within your bone marrow, there are cells, these hematopoietic stem cells, and they're always renewing, always making more. As they begin to divide, they have a choice to make, and this is under hormonal control. They'll either become lymphoid stem cells or they'll become myeloid stem cells. Lymphoid stem cells only become lymphocytes, and myeloid stem cells become all the other ones. So lymphoid stem cells only become lymphocytes, and myeloid, my writing's getting worse, all others. Okay. Now, every one of these sequences has a similar set of terms. So once you see them, you'll start to see a pattern here. The lymphoid stem cells will become lymphocytes. To get there, they go into lymphoblasts. Now that word speaks to us. We've seen osteoblasts become osteocytes. We've seen chondroblasts become chondrocytes. So we shouldn't be scared by this word. So lymphoblasts are then going to become pro-lymphocytes, and then they become lymphocytes. Basically, we're just looking at a maturation process. So first, from the bone marrow, there's the hematopoietic stem cell. That cell chooses to go become a lymphoid stem cell. The lymphoid stem cell then becomes a lymphoblast, then a pro-lymphocyte, and then a mature lymphocyte. You're going to see the same progression as we go through this. Now, what's going to cause cells to develop are called colony-stimulating factors. And these are basically hormones. Okay, so just kind of, that's just a fancy word for a group of hormones. And these hormones are going to specifically turn on and activate these lymphocytes. Okay, so the CSF, okay, you'll hear this word CSF, colony stimulating factors, not cerebrospinal fluid here, right? Colony stimulating factors. Now on the other side, it's the same story. On the myeloid side, it's the same idea. Again, these cells will become one of 3 types of progenitors. And I'll show you a picture in a moment. They are going to go into either monoblasts. Now, what are monoblasts going to become? Monocytes, right? Or they're going to go into a myeloblast. Okay. So the megakaryocytes we know are the huge cells. That's where they get their name. Mega, karyo, huge nucleus. And they're going to break apart and fragment off to form the platelets. Those are going to differentiate into proerythroblasts and then eventually into, I just messed up. So let me repeat this. So on the myeloid stem cells, either we're going to become a monoblasts, okay, a megakaryocyte, or a proerythroblast. Okay, sorry. Read my own writing. So let me help you with this. The myeloid stem cells, the blast we know is the precursor cell, and the monoblast will go to promonocytes. The promonocytes will become monocytes. So again, we're going to see the same words over and over and over. The myeloblast will become myelocytes, and the proerythroblast will go on to become erythroblasts. And then eventually reticulocytes. Reticulocytes will become red blood cells. Sounds like a lot of detail, but the picture will help you with this in a moment. Here's that hormone that I mentioned, erythropoietin, erythropoietin. You'll hear it pronounced both ways, EPO. And this is released from the kidneys. When we were doing endocrine, I didn't focus on the kidney at all. But the kidney does release some hormones, this being one of them, EPO. So the kidney could be considered endocrine. And EPO is released from the kidney under low oxygen situations. What's called hypoxia, hypoxia, right? Hypoxia is low oxygen. Now the kidneys are monitoring this oxygenation. And when that oxygen goes low, again, they are going to release EPO. And what's EPO going to do? Travel from the kidney, go to the bone marrow, tell the bone marrow to make more red blood cells. More red blood cells will now increase the ability of oxygen to be carried around and therefore restore the low oxygen situation. So beautiful little system. What would cause erythropoietin to be released? You're anemic, right? So you already have low red blood cells. That's what anemia is. Anemia is when your hematocrit level is low or when you have lower than normal red blood cells. So that's going to kick up EPO. The body's going to try to restore that and give you more or a higher hematocrit. If there's decreased blood flow to the kidneys, if there's some sort of blockage or some sort of ischemia, something going to the kidneys, that can also tell the kidneys to make more. Also, if there's decreased oxygen in the air, so let's say you're going to Denver, right? And as a result, there's less atmospheric pressure, and you actually get more or less oxygen in your body's going to perceive it as a deficiency in oxygen, and your kidneys will make more EPO. Okay? And if there's damage to the lungs, that makes sense. If the lungs aren't well, then you wouldn't be getting enough oxygen in the first place. Now, what if today I flew out to Denver and my body started to say, hey, you don't have enough oxygen right now, so the body's going to start making more erythropoietin. At some point, it might actually overshoot and give me a higher number of red blood cells than my body would initially need. Now, I've already introduced the word to you, anemia. You know that one, when red blood cell numbers are low. But a term that I'll mention in lab, that I want to mention here too, what if your body was overproducing EPO or sort of overcorrected for this and made too many red blood cells? Your hematocrit was above the normal limit. then we would say that you have polycythemia. Now, polycythemia usually isn't an issue. It can become an issue, but not that often. Anemia is a big deal, right? Your red blood cell counts are low, you feel kind of crappy, you don't have enough oxygen. Polycythemia, the biggest thing it can do is make your blood thicker. Does that make sense? If you've got too many red blood cells, that can thicken the viscosity of your blood. And now what's the problem? Blood's not going to travel through the capillaries as efficiently and could even lead to some issues, so clotting issues. So having too many red blood cells is also a problem. We want our rates to be, our hematocrits to be at an ideal number. But typically polycythemia is not a big issue because it's usually not long term. If you overshot and had a little bit of a high hematocrit for a while, the body will simply kind of restore itself. So it's rarely a chronic condition. Okay? Rarely is this polycythemia a chronic condition. Now, that's the EPO story. Now, the myeloid cells can become a promonocyte. Those become monocytes. But then there are also three types of band cells that are formed. And you're going to learn about these tonight and this week as well. These are the neutrophils, the eosinophils, and the basophils. Okay. And those also come from the myeloid stem cells. And those megakaryocytes are going to shed these little fragments that we're going to call platelets. And again, the erythrocytes reticulocytes. Reticulocytes become erythrocytes. So we'll see that term over and over and over, the reticulocytes. So here's the big chart, just to get the general idea. Not to memorize it. I'm not going to ask you to take it apart or anything. But let's just take a look here. Follow along with me. So I've got, again, I'm just kind of expanding what I had before. Here's that hematopoietic stem cell. It's that cell that can become anything. The word we use for that is multipotent, right? So it can become anything. It has the potential to become many different kinds of cells. Multipotent. It makes a choice. The fork in the road, the first fork is either I'm going to be lymphoid or I'm going to be myeloid. If it becomes lymphoid, straight across the top, right? It only becomes lymphocytes. It's going to become first a lymphoblast. We had that slide earlier. Goes to a lymphocyte, and then finally a lymphocyte. Now that could be a T cell or a B cell. If you've taken micro, you'll learn a lot more about those cells. As we get to the immune system and the lymphatic system, we'll talk more about T cells and B cells. But your lymphocytes belong either, for the most part, they belong to either the T cell or the B cell family. If instead the cell chooses the myeloid stem cell, I shouldn't say chooses, right, but is forced to become through those hormones, then it has three first choices. Number one, it can go across the bottom and it can become a proerythroblast and eventually become a erythrocyte. This one's going to be pushed or stimulated by EPO, right? So erythropoietin is going to push the formation of your red blood cells across the bottom. This myeloid stem cell can also become a megakaryocyte. Megakaryocytes will bleb off and become the platelets, or form the platelets. And then in the middle, we see that this progenitor cell, this is the one that is stimulated by CSF. There's that colony stimulating factor. And that is going to cause you to get different band cells, and that's going to form neutrophils, eosinophils, and basophils. So we have all of the different, and I missed this one. And this progenitor cell can also go up and become a monoblast, which goes over to make the monocytes. So that's all your cells, right? That's all your formed elements. Across the top, we've got lymphocytes, then there's the monocytes, there's your three granulocytes, and then the erythrocytes and platelets at the bottom. So platelets are not cells at all, right? They're just little fragments of a megakaryocyte, and we already know that they are involved with blood clotting, and they're constantly made, as are red blood cells, right? Because they can't divide, because they can't say, okay, I need more platelets and make their own decision to divide. They are constantly being made in your bone marrow. Numbers are important. This will be important in lab, and I want you to know these ranges. So for platelets, here they're telling us about 350,000 or so platelets per microliter of blood. Now, 1 microliter of blood is equal to a cubic millimeter. You may see that verbiage used. The range here about 150,000 up to 500,000. In lab, I think I said 130 to 300,000. So again, we're still talking about the low hundreds of thousands, okay? So I'm not going to be nitpicky on this, but somewhere in the low hundreds of thousands is normal. Now, what if you were under 150 or under 130? Let's say you're under 100,000. Keep it simple. What if you had under 100,000 red blood or platelets per microliter of blood? What would your symptoms be? Trouble clotting, right? So when you cut yourself, you might bleed longer. What would you notice on that patient's hands or body? A lot of bruises. Why? Why the bruises? Why the bruises? Why the bruising? You, in your normal clumsy life, right, hit your hand and hit your body on things, and there's microcapillaries. There's capillaries that are going to bust when you hit something, and blood is going to release under your skin. Now, for a normal person, it's going to clot quickly, and you're not going to notice it. But in a person with low platelets, when they just naturally hit their hand against the dresser or whatever, that little bit of blood flow, right, is not going to stop and is going to ooze out and cause more of that sort of bruising appearance.
So that's where everything comes in, where it's not.
So the platelets release clotting factors, and there's already fibrinogen in the blood. They work together. We'll see that. And but if you have low platelets, then you're not going to activate your blood clotting cascade the way you should. But I mean, honestly, every time you just walk around, you're knocking up against things. There's going to be capillaries that burst, but that blood is going to clot in you and me very, very quickly. We're not going to notice that.
So that's where blue bloods come from,
Basically, right? So those big old, bruises that you see on the elderly are in part because of decreased clotting time and increased bleeding time, okay, from a decreased number of platelets. Okay, so that gets us through a little bit about the platelets, kind of where they're coming from, right? Where are they coming from? And now let's move into a little bit more specifics about each of these cells. We're going to start off with red blood cells for the first section. Then we'll move into some blood typing, your favorite thing, and we'll finish up with white cells and clotting. I will expect you to know blood clotting or blood typing. Now, that was a 105 thing, and I'll quickly review it with you this semester. Hopefully, that story is making sense to you, but we won't be talking about it in lab. So if you were having some sort of blood disorder, you might be sent to a hematologist. This is the study of hematology. There's a lot of interesting diseases related to the blood. It's amazing what the blood can tell you about your overall health. And everything from clotting disorders to infection to anemia to overall well-being can be told by your blood. So you go to the doctor, and they might evaluate a few things. They might do a CBC, a complete blood count. When they do a CBC, they're going to be looking at everything, right? They're going to be looking at your red blood cell count, okay? If they know your red blood cell count, then they can do your hematocrit. They're going to be looking at your white blood cell count, okay? And they're going to do a differential. They're going to figure out how many of those white blood cells you have. In lab tonight, we'll talk about the normal ranges. How many neutrophils should you have? How many eosinophils, basophils should you have in your blood? They're also going to look at your hemoglobin content. They're going to look at your, even the size of your white blood cell, of your red blood cells. So they're even going to see if your red blood cells are looking healthy, if they're normal size, if they're a little crenated, if they're a little bit swollen. That's going to tell you about what? If your red blood cells are crenated, what does it tell you? Just in general, that the plasma is too it's hypertonic, right? Water's being drawn out of the red blood cells. So that might suggest that your electrolytes are a little bit off if your red blood cells are kind of crenated. What if they're a little bit plump? Hypotonic, right? So again, we can look, when they do a CBC, they're looking at a lot of things. And for most people, it's normal. It's kind of boring. But there's a lot of things that can be told about a person's overall well-being by looking at some of these very specific things in a CBC. We won't be going to all of it, but I'll help you appreciate some of it. So here are some normal numbers. Okay, this is what we're looking at. So hematocrit, so we do a CBC, and we get a hematocrit back. What does a hematocrit tell you and me? I need you to understand what these things tell us. So what does hematocrit tell you? The percentage of the blood made up of red blood cells. So a hematocrit of 42% tells us that 42% of this patient's blood is red blood cells. Is that normal? For a female? Yes. For a male? A little bit low, right? So if this was a male, they'd be anemic. If they were female, they'd be normal. We're also looking at hemoglobin. I'm not going to give you the normal value of that, but we can tell the hemoglobin. That can be high or low. What if hemoglobin's low? Then your red blood cells aren't able to carry oxygen as efficiently as they should. We're going to be looking at MCH and MCV. I'll come back to those. MCV has to do with the volume of the cells, how plump they are, how crenated they are. It's going to look at the platelet count, 350,000. That's his per millimeter cubed. Other name for that is microliter, right? Same thing. And that's normal, right? That was right on the normal number I think they gave us. Red blood cells, 5.2 million per microliter. So that's a raw number of red blood cells. In lab today, I'll give you a raw range of red blood cells as well as the normal hematocrit values. That's normal. White blood cells, 7,000 per microliter. I haven't said this yet, but the normal is 5,000 to 10,000. So that number's right in the middle, right? You should have between 5,000 and 10,000 white blood cells. Here we have 7,000. And then it goes on to give us a white blood cell differential. For those who were in lab this afternoon, okay, if you haven't been there yet, it's okay. Those who were in lab this afternoon, neutrophils at 67%. What do you think? Yeah, okay, right? What did we say? 50 to 65, okay, plus there could be some bands that could add up to about 70. So 70-ish, 65, 70, it's okay. How about lymphocytes? Should be between 25 and 33, check. Monocytes between 3 and 8, check. Eosinophils between 2 and 4, check. And basophils 1 or less, check. So this person, right, is looking pretty good, especially if this is a female, right? A little anemic if it's a male. That's what I want you to be able to appreciate. If I were to give you something like this, don't worry about MCH and MCV right now. But if I gave you the other numbers, either in lecture or in lab, by the time you finish this week and go through lab, you will appreciate if this is normal or not. And you'll also understand what the condition might be, okay? So more on that tonight for those who are having lab or on Thursday. Now, when you're doing red blood cells, again, not only are we looking at the number of red blood cells, we're also going to look at their size. So I'm going to come back to that. We're going to be looking at their shape, and we're going to be looking at their maturation, their maturity. If you have a lot of immature red blood cells, right, or not very many, it could tell you about the overall condition. And also from here, we can also tell by looking at those numbers, we can also tell things that aren't even obvious, like, do you have some internal bleeding? If you've got internal bleeding, what might you see in a CBC? If you're losing blood, unknowingly, right? Stool in the blood, didn't notice it, whatever, but you've got internal bleeding, what's going to happen? What's going to happen to your overall blood count? It's going to go down, right? So you may not even know it, but there could be some internal bleeding, and the blood test would indicate that something else is going on. So here are some numbers for you. I do want you to take a look at these. So I know it's small. So hematocrit, again, 37 to 54. That's across all individuals, isn't it? I'm not differentiating male and female here. Hemoglobin concentration, 12 to 18 is normal. So grab that number, 12 to 18 hemoglobin. What was our patient a moment ago? 14 something, so they were normal. Mean corpuscular hemoglobin concentration. This is looking at your hemoglobin concentration, MCH. See the H in it? Hemoglobin. Okay? And normal 27 to 34. Now, what's cool about this is that what does hemoglobin, what color is hemoglobin? Red. This is actually a measure of how bright the redness is. If the hemoglobin is in the normal range, then we say that the cells are normochromic. What does chromo mean? Color. Normal color. Normal chromo. Okay, chromic. If there's an elevated MCH, then the colors of the cells would be hyperchromic, more red, a brighter red, literally. Okay, so they're actually looking at the concentration of hemoglobin based upon the color of the cell. And then if there wasn't enough, then you would be hypochromic, not as red of a cell. I used these words earlier, but I forgot to go to the side. What if your hemoglobin or your hematocrit is low? Anemia. And if it's high, polycythemia. What if, and then the next one, MCV, mean corpuscular volume. It's now measuring the volume, literally it's measuring the volume of each little red blood cell. Pretty amazing that they do this. But a normal volume, 82 to 101. Don't memorize the number, okay? But what if the cells are a little bit larger? We would say the cells are macrocytic. You know that as what? Cells getting larger because it's in what kind of environment? Hypotonic, right? And if instead the cell was microcytic, we would have called it last semester crenated. It's smaller, right? And we know that the environment would be hypertonic. So the size of the cell, don't memorize the number, right? But if you see this word micro or macrocytic, we're referring to the size, right? Big cell, macrocytic, macrocyte, right? Big cell, little cell. Rough red blood cell count. Between 4 and 6 million or so red blood cell count, or red blood cells per microliter. And then finally, reticulocytes. Reticulocytes are immature red blood cells. Okay, so as red blood cells are being formed, there will be some reticulocytes in your blood. But the normal range should be less than 0.8%, about 1%. Now, why 0.8? Help me with this. I'm jumping ahead a little bit, but how long does the average red blood cell hang around? 120 days. So where's that 0.8% coming from? What if a red blood cell lasted for 100 days? Right? And I said that reticulocytes were 1%. You with me? So that 120 days, basically how long does a red blood cell stay a reticulocyte? 1 day. Right? So they're constantly being made, and there's 1 day's worth of reticulocytes in your bloodstream. Normally 0.8%, right? So if 120 days is the average lifespan, 0.8% would be 1 day or so out of every 120 days, you've got some reticulocytes. If you had too many reticulocytes, reticulocytosis, what might be going on? What would cause reticulocytosis? Making a lot of new blood. She said you're losing a lot of blood. That could be. I was thinking, that's not wrong. I was thinking I just hopped on a plane to Denver. Right? And I'm going to a higher altitude. And as a result, my body's going to kick up EPO and make a lot of new red blood cells. So there would be a higher than normal number of early, immature red blood cells floating in my blood. So I would have reticulocytosis for a day or two, right, as my body is adjusting to the higher altitude. And then what if they were low? Right? There's no really fancy word for this. Diminished erythropoiesis. It means what? That your body is not making adequate red blood cells for whatever reason, right? Whatever the reason is. So a lot of stuff, right? A lot of stuff that we can figure out. But I hope you have the tools. I hope you have the background now to appreciate some of this. Right? We've been talking about some of these terms in different ways, but the larger or smaller cell, right, and what's going on. So take a look at that. Let me know if that's not making sense to you as you review this. Red blood cells, we know the most about these cells. They account for 1/3 of all of the cells in your body. I mean, it's just amazing. Right? Of the trillions of cells in your body, 1/3 of them are red blood cells. They're constantly being made. You've got millions of them in every drop of blood. It's a phenomenal number of cells. A single drop of blood, 260 or so million red blood cells. You get about 25 trillion cells. So how many cells do you have in your body? If these are 1/3. About 75 trillion, right? 75 trillion is kind of that number you'll hear. In your body, about 75 trillion cells. So there are the numbers, right? An average male, 4.5 to 6.3. In the lab, I think I said 4.2. So again, don't get crazy on these. But I always kind of say 4 to 6 million in my own head. 4 to 6 million red blood cells. Women, okay, fewer, right? Fewer. So if I took a smear of blood, what am I likely going to see? There could be places where I only see red blood cells, right? I don't see anything else. I only see red blood cell because they're 99.9% of the formed elements. So you might have to go looking for white blood cells. You may have to go looking for platelets, especially since they're smaller. But here, I'm pretty much just seeing red blood cells, maybe a few platelets thrown in there. But I see nothing obviously that looks like a white blood cell. Your eye will become trained to understand that as we go through this. What's the shape of a red blood cell? Biconcave is the word we're using. That means that it kind of looks like this, right? Like a dog bone. It has a double indentation. That's the biconcave portion. It has a very distinct diameter. This book has this, here I rounded it up, but 8 micrometers or 7.5. You'll see them both. Okay. 7.5 to 8 micrometers. They basically become like a little ruler inside the microscope. As you're looking at samples, if you look at a blood vessel and you see a little red blood cell in there, you know, okay, that's about 8 micrometers, 7.5 micrometers. It kind of creates its own little internal ruler when you're looking at cells. These are anucleated. Mature red blood cells have no nucleus. So as cells go from reticulocytes to mature erythrocytes, they lose their nucleus. No more nucleus, no more division, no more cell division, no more ability to divide. They hang around for about 120 days. So because they also lose their other organelles. So not only do they lose their nucleus, they lose their ribosomes, they lose their mitochondria, they pretty much lose everything. So they have really no metabolism, and they can't divide, they can't repair themselves, and they hang around for about 120 days. And then what organs are constantly sucking them up and recycling them? Liver and spleen. So liver and spleen will be two organs that will be picking up these red blood cells and sort of determining that they're getting old. So there is the very specific dimensions, 7.2 to 8, right, 0.4. But if you just remember 7.5 to 8 micrometers, that's the number I need you to remember. Okay, 7.5 to 8 micrometers. So this biconcave shape actually gives an advantage to the function of the red blood cell. This actually increases the surface area. Okay, so by having these two indentations, the two biconcave sides, you actually increase the surface area. And this is important because we have to diffuse oxygen. And diffusion is dependent upon the surface area of the cell. So the greater the surface area, the more diffusion of oxygen that can occur. Now, it's also possible for red blood cells to form a stack. So as they're going through like a small capillary, you'll see them almost you'll see pictures where it's almost like they're stacked on top of each other like little poker chips. And that's called rouleau. Rouleau. I think of Rolos. Is it Rolos? Yeah. Little stacked discs, candy. It works, right? Little Rolos, right? And you know already that red blood cells are flexible. So you know that you've seen them change diameter when You saw them crenate and swell a little bit in lab under hypo and hypertonic solutions. And they do the same thing. In your body, they can also kind of change shape, kind of wiggle their way through capillaries. So again, red blood cells, really cool. They have a large surface area to volume. They can stack, and they're flexible. This is all important stuff as you consider their job of carrying blood and oxygen through your body. So here's a rouleau. You can see them kind of stacked in like poker chips. Okay, there's a little stack. There's a little stack right here. So they can really kind of stack up and go right through very small capillaries. That also increases the number going through a small area. The number one thing to remember about, there's actually two important proteins in red blood cells. One of them is hemoglobin. Hemoglobin is the big one. That's the one that's carrying the gases. You'll see HB or HGB as abbreviations for hemoglobin. And 95% of the red blood cells' proteins inside are hemoglobin. Now, what did I just tell you? The red blood cells have lost their nucleus and they've lost their ribosomes. So that means that mature red blood cells had to have already had, right, these hemoglobin molecules in there. The hemoglobin molecules are made by the precursor, right? They have to be. And then as the red blood cell matures, it loses its ribosomes, it loses its nucleus. It no longer can make the hemoglobin. Range, there it is. Male, 14 to 18. Female, 12 to 16. And that number was also in that table as far as range. And who has that table right in front of them? What was that range? Did it say 12 to 16 on that? Or 12 to 18?
Yeah.
Yeah, 12 to 18, so male and female. All right, 12 to 18. Now, what is hemoglobin? It is a protein made up of 4 subunits, 4 parts, and not very imaginative. There's alpha 1 and alpha 2. There's 2 alphas, I should say, and there's 2 betas. There's a first beta, there's another beta over here. Each of those chains has in the center a heme group. In this cartoon, the heme group looks like a little coin. That's a heme group. And in the very center of that heme group, you see a little red circle. That red circle is the iron ion. So heme binds iron, and iron is then what binds the oxygen. Okay? So we need to have iron to bind oxygen. This is why, another way of thinking about anemia, if you want to increase your red blood cells, eat spinach. Right? Why? Iron. If you are iron deficient, then you cannot make the red blood cells that your body requires. So your number of red blood cells may be okay, but your hemoglobin would be low if you were low iron. And regardless, you would still be considered anemic. Right? So low red blood cells, low hemoglobin, low iron, all connected, all leading to the same diagnosis of anemia. So we say that there's 2 alpha chains, 2 beta chains. That would be the quaternary structure. Do you remember this story? So in proteins, if I had one amino acid, another amino acid, another amino acid in a chain, just made off the ribosome, right? Translation. We would call that chain of amino acids the primary structure. And then that chain of amino acids would fold and twist a little bit on itself, and we would call that the secondary. So it could kind of make into like a helix. Okay, we'll kind of imagine the protein makes into a helix. That'd be the secondary structure. The tertiary structure is the final structure of the protein. So if this were an enzyme, the tertiary structure would be the shape of the protein that gives the enzyme its function. That's usually all we talk about, primary, secondary, and tertiary structure. But because this is a protein made up of 4 smaller subunits, we now use the term quaternary structure, which means it's the complete little subunit combined into this little foursome. So that's this whole idea of a quaternary structure. Okay, quaternary. And again, each chain has a heme group. That heme group is a pigment. Now you see where the word gets hemoglobin as its name. Globin describes the shape of the protein. It's a globe. It's kind of spherical. And heme being the group in the middle of it that attaches the iron and binds oxygen. So that's where we get the word hemoglobin. It truly is 4 globins. Let me go back. 4 kind of spherical globins with a heme group in the middle. Okay, hemoglobin. Now that iron group is really, really important, and when hemoglobin is bound to oxygen, we call it oxyhemoglobin. Question?
How does iron make your red blood count?
Okay, so without iron, let's say you're low iron, then you don't have the building blocks to make the hemoglobin. Okay, so your body might be shoving out red blood cells, trying to, but red blood cells themselves have to make the hemoglobin, and if there isn't enough iron around, then you will be hemoglobin deficient, which clinically is going to be the same as having low red blood cells. Okay, you just don't have the building blocks. So by adding more iron, you'll correct that and increase the number of red blood cells. Okay, so that's where iron and hemoglobin and hematocrit, if you're low in any of them, anemia, right? It's the same diagnosis. Low iron, low red cells, low hematocrit, or low hemoglobin. So when hemoglobin, okay, back up. Each hemoglobin has 4 hemes, and each heme can bind 1 iron, and each iron can bind 1 oxygen molecule. The more oxygen that's bound, the redder the hemoglobin. The maximum number of oxygens that can bind to a hemoglobin is 4. And when all 4 oxygens are bound to hemoglobin, it shines bright red. So oxygenated blood is red, right? Bright red. If there is fewer than 4 or none at all, then the blood becomes darker in color. And if there's no oxygen at all bound to the hemoglobin, we call it deoxyhemoglobin. So oxyhemoglobin has oxygen bound, deoxyhemoglobin has no oxygen bound, and it what? Is not bright red, but instead a dark red, kind of more of a, I don't know, a brick red color. It's not blue. Now we call it blue blood. We draw it as blue blood in manuals and books. And part of the reason we chose blue is because the color that one sees through their skin. Venous blood looks kind of bluish to us through the skin. That's why we chose that color for models. But it's really not blue. It's simply this dark red color. So not to memorize this, just realize this is the heme group. That's that sort of little coin-shaped structure, and the iron molecule right there in the very center of it. And there's 4 of those heme groups in a total hemoglobin, 1 heme group for each globin. Now, this is where the numbers also get kind of astronomical. Each red blood cell contains 280 million hemoglobin molecules. Okay, so each red blood cell has within it 280 million hemoglobin molecules. And each hemoglobin, we know, can bind 4 heme or 4 oxygens. Most of the oxygen that you carry through your blood is because it's attached to hemoglobin. 98.5%. So the vast majority of your oxygen in your body right now is traveling attached to hemoglobin. The other 1.5% is dissolved in the plasma, just simply dissolved, not attached to the hemoglobin, but just dissolved straight into the fluid compartment. Okay, so a little bit about red blood cells, and I think we got this. I really do. I've already said to you that red blood cells hang around for about 120 days, which means what? About 1%, roughly, or about 0.8% to be really specific, about 0.8% are being replaced every day. That means that you are destroying, right, that many as well. Again, the liver and spleen are helping to destroy those cells, and that also numerically means that you are creating about 3 million new red blood cells every second. Astronomical, right? You just made 3,000 or 3 million more red blood cells every second. Again, you got to keep cranking them out because the lifespan is so small, or so short, relatively short, 120 days, about 4 months. But it's because of the sheer number, right? 1/3 of your body's cells are red blood cells. And we've already said that these cells are, when they're used up their livelihood, the spleen, as blood is going through the spleen, as blood is going through the liver and the spleen are kind of checking out. And if the red blood cells are kind of looking old, it's like our circulation with $1 bills. They start getting old. We take them out of circulation. We destroy them. The macrophages that are found in the liver and the spleen are chewing up those old, dying red blood cells. I should say dying, right? Are they even alive? You could argue they're not even alive because they don't have a nucleus, but they're going to chew up those old red blood cells. Then that heme group is recycled. So we don't, when the liver and spleen destroys the red blood cell, it's going to recycle that iron because we can't afford to lose iron. Iron is hard to come by. Now, the whole process of making red blood cells is erythropoiesis. We've seen that erythropoietin, right? The hormone that causes this to happen. The process is erythropoiesis, and it happens only in the red bone marrow by what kind of tissue? Myeloid, right? Myeloid was the branch that made all of the cells except for the lymphocytes. Where are you still making red blood cells? I should say, not just red blood cells. Where are you making any blood cells? Where's your red bone marrow? As an adult, your red bone marrow is still only in proximal head of your humerus, proximal head of your femur, ribs, vertebra, frontal bone. That's where most of this is happening, right? What did I miss? Yeah, a little bit of the scapula, a little bit in the pelvis, the os coxa.
So when it says skull, it's the
Frontal bone, most of the flat bones. It's mostly the flat bones. If you look at this list, so it's ribs, it's sternum. Frontal bone is a flat bone, even though it's curved, right? It's still a flat bone, as is the parietal. So really, just the flat bones of the skull. Frontal, I always say frontal. It's always amazing to think you got blood being made right here, right? It kind of just seems odd. And the rest of it, right? The rest of the bone marrow has been converted in you to yellow bone marrow. But it's neat. It can revert. So if I took a chunk of yellow, if your body needs, let me put it this way, if your body needed more red bone marrow, the yellow bone marrow can revert back to become red. So once red becomes yellow, it can go back if needed to increase the rate. So if you had a major blood loss or for some reason, some of that yellow bone marrow can actually convert back to red and start making blood cells. So what happens here, and I'll talk to you about that reticulocyte again. We glossed over it earlier. So red blood cells must absorb iron, right? Makes sense, because the red blood cells are making 280 million molecules of hemoglobin per cell, and you're making 3 million of these cells every second. So the body needs iron, and that iron is absorbed into these cells. And the red blood cell is going to go through the following stages: pro-erythroblast, okay, blast making, then a basophilic erythroblast. I'll show this to you in a moment, but basophilic because it is kind of a darker color, and it's really heavily making hemoglobin at that point, so it's really colorful. Then it's going to become a normoblast. This is where it ejects its nucleus. So the normoblast ejects its nucleus and now becomes a reticulocyte. The reticulocyte does not have a nucleus, but it's still, now it starts to go into circulation. And it tells you at the bottom bullet, after 24 hours in circulation, it becomes a mature red blood cell. Does that now make sense why it said 0.8% of your cells should be reticulocytes? I said 1 day, right? 1 day. So as the red blood cells are being made, they spit out these reticulocytes. It takes 1 day for them to become mature red blood cells, and that accounts for that 0.8% of your red blood cells being reticulocytes. So here's just a picture of all that good stuff. So again, from the bone marrow, this is, what bone is this? Come on. Humerus, right? Proximal of the humerus. So we got some red bone marrow in there. So we're going to be making some proerythroblasts. Then you can kind of see they get really colorful. They also get smaller. Notice that the cell's getting smaller and smaller and smaller as it goes down this process. And there's that normal blast. The normal blast kicks out the nucleus. It just gets recycled. And then becomes the reticulocyte. And then the reticulocyte will become the mature red blood cell. 120 days is the lifespan. These cells are going to kick out. Spleen, liver, and some bone marrow is also going to be cleansing and monitoring these. And we're going to say that they're destroyed by hemolysis, right? The breakdown, the lysis of the red blood cells. This is going to remove the hemoglobin. So the hemoglobin is going to be removed. The cellular fragments will be broken down by the macrophages. But now that hemoglobin needs to be recycled. That iron is really important. We all know we need a certain amount of iron in our body. Too much iron is not good, right? One of the major causes for kids, hospital visits is overeating their iron-enriched Flintstone vitamins kind of stuff. So too much iron is not good. It's toxic. But iron is also poorly absorbed. It's kind of a weird story. We'll get into it a little bit later. But we can't lose that iron, especially when you think about the sheer number of iron molecules that are being made and recycled every day. So we're going to recycle this stuff. And it's going to be released into the bloodstream, but it's going to be carried by a plasma protein called transferrin. Transport. Ferrous is iron. N on the end, it's a protein. So transferrin is a protein that carries iron. And it's going to float around the body, and then also the heme is going to get broken down. Now, as heme gets broken down, this is actually what gives your urine and your feces their color, in part, is the breakdown of the hemoglobin. So the heme will be broken down and will be called biliverdin and then bilirubin and then go to the bloodstream. This is why 2 bruises change lovely colors. What's verde? Green, right? When you're bruising, when you have a big bruise, the first color is kind of that greenish tinge to it, and then it goes through different colors. So you're looking at the breakdown, the recycling of the blood in a bruise. If there is hemoglobin that is not broken down, will get eliminated in the urine, and that's going to give your urine its yellow color. If there's a huge number of red blood cells being broken down at the same time for some reason, that can certainly color your urine darker red or brown, which is of concern. Okay, and then you would have hemoglobinuria, which is what? Urine with hemoglobin in it. So if you're, for some reason, breaking down lots of red blood cells, and we'll talk about different urine conditions in the last lab of the semester. We'll be doing a urine lab. We'll be looking at glucose and bilirubin and other things in the urine. Oops. So just to take a picture of this whole thing. So the macrophages in your spleen and your liver, a few in your bone marrow, are going to be breaking down red blood cells. So here's a red blood cell. It's being brought in. That red blood cell is going to be broken down. The heme is going to be recycled down to bilirubin, and the iron will be transported in your blood by transferrin and recycled around. So just kind of look at that image. It'll help you figure out what I've just said. So the bilirubin is going to be released from the macrophages and is going to be transported to the liver, and that's going to give your bile its color as well. So bilirubin and bile have that BIL in them all because it's related. So the coloring of your bile, what color is bile? Kind of a green, right? Kind of a green, dark color. And what if the blocked bile ducts? What happens if someone has a blocked bile duct? It increases, and now we say they have jaundice. So if you have jaundice, this can be a yellowish coloring to your eyes, a yellowish coloring to your skin, and that's going to be an increase in bile. So what's happening? The body's always breaking down red blood cells, right? Constantly, 3 million every second. And if it can't get back to the liver properly, then that stuff is accumulating, right? And that turns into the yellow skin and the yellow eyes. So that tells you the liver is not functioning properly. So if you have jaundice, the liver is not functioning, either because the liver itself is sick or because there's a blockage of the duct.
So is the bilirubin more green and then the bilirubin is yellow?
Yes. So the biliverde, right? Verde, green. Yep. Yep. So what else is happening? Bacteria in your gut are going to be converting that bilirubin into other molecules. Don't worry about the names of them, right? But they're going to be part of your feces. And this is going to give your feces their yellowish brown color. Again, it's from the breakdown products of your red blood cells. You're also going to be releasing some of this into your urine. That's going to give the urine the yellow color. And if you had intact red blood cells in your urine, not a good idea, right? Typically you wouldn't, but if you had red blood cells in your urine, then you would have hematuria, saying that you have hemato, right, blood cells in your urine. That would be the cause, usually caused by some sort of kidney damage or a urinary tract infection. So just to get a visual on this, so again, that bilirubin is traveling, it goes to the liver. And if it can't get to the liver, what's going to happen? It's going to build up, right? Either the liver's sick, or if that bile duct is blocked, then you're going to have jaundice. The bilirubin goes to the liver, and it's going to continue to break down, part of it in the bile going to the feces. So that bilirubin goes into the intestine and out. And also, some of that is absorbed in the bloodstream, which gives the urine itself the yellow color.
Why would it get absorbed into the bloodstream?
What is that? These urobilin right here.
Yeah.
This urobilin molecule, question was, why does it get reabsorbed? It just does. There's so much of it in the intestine that some of it actually gets absorbed in the bloodstream, and then from the bloodstream it's being filtered out by the kidney. There's just so much of it. Just think volume. There's just, diffusion. There's just so much of this stuff. The body has to get rid of it, and it's going to choose the kidneys as well as the feces to try to get rid of some of this waste product. This is just kind of puts the whole story into one slide. So there's basically the two slides that we've already seen, but what it does is it connects the red blood cell. So here we got the red blood cell being made, the reticulocyte going out into the bloodstream, becoming a mature red blood cell, floats around for 120 days, and then is recycled. So this figure is nice. This is 17.6. Kind of puts the whole thing in perspective for you. Okay, blood type. I'm going to jump over this pretty quickly. Let me just kind of quiz you. What are the different antigens that can be on a red blood cell? A or B or and RH. Good. From those three different antigens, how many blood types are there? O positive, O negative, A positive, A negative, B negative, B positive, and AB positive, AB negative. So 8 different blood types, right? Okay. Where do we get these antigens? These A, Bs, and RHs, we got them from our parents, right? We inherited these things. These things are part of our being, and they help identify our blood cells. And why do we care? Blood transfusions, right? It's all about blood transfusions. You can receive blood that your body says, I've seen this before. and you could not receive blood that your body senses as being foreign. And so that's really what's important, is recognizing which blood types we can and cannot receive. So again, here are the antigens, A, B, AB, both of them simultaneously there, or type O. Type O is not an antigen, it's just the absence of either A or B. What happens in your body if you receive the wrong blood type? What's going to attack the wrong blood cells? Antibodies, right? And those antibodies, let's pull this all together, are actually made by some of the B lymphocytes, right? Some of these lymphocytes that make antibodies. So your body has a collection of antibodies floating through it, really a vast arrangement of antibodies. And those antibodies are there to protect you from foreign antigens. So looking at a table like this, if you have type A, you inherited type A from your parents, you would naturally have antibodies against the other type of blood. You would have antibodies against B. If instead you inherited type B from your parents, you would have type A antibodies. You would have antibodies against foreign blood A. If you inherited both A and B from your parents, you would have neither antibody, right? They're normal for you. You're not going to fight yourself. And if you did not inherit either, you've got naked little red blood cells, you have type O. And type O, you don't have A or B, therefore your body would make A and B antibodies to fight off those foreign antigens. So when the wrong blood is entering your body, the antibody will bind to it. That's called agglutination. And agglutination can lead to a clotting, a blockage of blood. That's what's so damaging, is that blockage of blood, if it's going to part of your brain, liver, kidney, heart, some critical organ, then that could be a life-threatening issue. If it's just blocking the blood into your pinky, not the biggest thing, but you still would be sustaining tissue damage. Okay. Now, the other antigen, in addition to A, B, and O, or A and B, is the Rh antigen. It is oftentimes called the D antigen as well, so don't be thrown off by that. If you have the Rh antigen, it's because you inherited it, no big deal, and you have one of the positive blood types. If instead you did not inherit the Rh antigen, you have one of the negative blood types. So A positive, you have the Rh. A negative, you don't. It's not right or wrong, it just is. And here's, not to memorize this, but there are differences in racial profiles of blood antigens. If at a crime scene they find a particular blood type, it cannot indicate, right, race, but it could at least, I guess statistically, help them look. If you found at a crime scene, let's take a look here. Which one's really out of whack? Let's see if I can remember which one is really out of whack here. Yeah, Native South American. Oh, okay, there we go. Right? If you found, thank you. If you found native, if you found type A blood, right, and you were a forensic scientist in South America, right, you could pretty much what? Eliminate a native, right? Because they're 100%. So in other words, it's just a small group of people. They all have type O, right? That'd be a pure, purebred population. In the United States, what do we have? Look at these numbers. It's not majorly different, is it? Type B, you'll see the B antigen in 11% of Caucasians, 20% of African Americans, 30% of Koreans, okay, Korean Americans. So there's some variations. Don't memorize this. It's just kind of a fun thing to look at. What I do want you to see, though, of all the blood types, what's the most common? O, and the most rare? AB. That I do want you to appreciate, right? So O is the most common, and AB is the most rare. And what's more common, A positive or negative bloods? 85% of us in this room are one of the positive blood types, right? So on average, 85% are Rh positive. So I will be doing a there will be at least be a couple questions on the test for sure about blood typing. So look over that. If you're struggling with blood typing, would you let me know next week in lab, and I'll walk you through it, okay? If it's just never clicked before, or you're looking back at it and saying, I don't remember how to go about this, please let me know. Otherwise, I'm going to jump ahead through this because this is something you really should have an understanding of. There is the hemolytic disease of the newborn. This is probably the most clinically relevant, besides just blood transfusions. Hemolytic disease of the newborn, HDN, is when a child is born to a woman of the wrong blood type, if you will. So if a woman is Rh negative and her husband is Rh positive, the baby is Rh positive, what's the problem? First baby, what's the problem? Is there any problem with the first baby? No. Right, no problem. But birth is messy, and there's always going to be some of the blood, a baby's blood, that's going to pass into the mother's circulation. And that foreign blood is now going to be setting up an immune response by the mother. So now the mother is going to start making antibodies against the Rh factor. Second baby comes along. If that second baby or the next baby that is Rh positive, the baby's blood will be attacked by the mother's antibodies. The antibodies can pass through the placental barrier and start attacking the baby. So that can lead to a huge problem and even kill and destroy the fetus. Okay, so pretty no longer an issue, because nowadays what do? We give the mom a shot called RhoGAM, and that RhoGAM shot basically eliminates the possibility of this being a problem. But in old days and in countries where they don't have that, then this is still a major issue. So that whole story is given to you here, okay? Now, this can be a huge fatality rate, or the newborn can be born extremely anemic. It makes sense because the mother is destroying its red blood cells, right? And also very jaundiced. So it's possible that the baby will survive this, but have some issues. Now, once they're born, it'll be okay, right? We can help the anemia, we can help the jaundice, but we've got to get through. We got to be born, right? Once they're born, I'm not sure if there's any problem. They can correct the problem. It's just getting out of the womb is the problem. Okay, so that's a little clinical story. Read through that. It's an interesting little story. Let's switch our attention to white blood cells. White blood cells. That's red blood cells. Anything at all? I'm going to give you a little break. Okay, so let's take about a 5-minute break and come back with any questions on red blood cells, and then we'll get through white blood cells and platelets, and that'll probably finish up today. I thought I'd get to some muscle, but I may not. Anything at all to pick up? I mean, I think it's mostly, I won't say all, mostly review, but there's a lot of review in there and a few new facts that I think make sense. Let's take a look at white blood cells. These are the leukocytes, and I'm not going to spend as much time here on the identification part because we're going to be doing that in lab. Honestly, I'm just not going to repeat it. So know that if you have lab tonight, you're going to hear it after the exam. Now, white blood cells share some properties of other cells. Number one, they only spend a short amount of time in circulation. Okay, mostly they go into your loose or dense connective tissues when infection occurs. So you got these white blood cells, they're circulating through your blood, and when you damage yourself or whatever, you know that you get an area of swelling, right? That swelling is where these white blood cells are going to help you out, and at that point the cells actually get out of the bloodstream and go into your connective tissues and hang out there and fight off the bacteria or the viruses or whatever it is that has gotten into your body. They migrate out of the bloodstream. They actually go up near the blood vessel, and the process is called emigration, or what you'll hear more is diapedesis. Diapedesis is the movement of or the transfer of a leukocyte out of the blood into the tissue. Now, how do they get there? They're being drawn by chemicals, right? All of these cells are being drawn by, these white cells are being drawn by chemicals. And we're going to call this positive chemotaxics. So they're positively being affected. They're being drawn toward, they're going toward certain chemicals. These chemicals, literally, bacteria send off chemicals. And those chemicals are going to attract white blood cells. parasites give off chemicals, and those chemicals are going to attract different white blood cells to come into your body or go to the site of infection. If it's said instead negative chemotaxis, the cells would not be drawn there, but it would basically retard them, right? Tell them to go away. So positive chemotaxis draws cells in, negative chemotaxis would send cells away.
Is there any kind of like diseases or anything that do that?
They do that?
Yeah.
Certain cells are definitely sent away, yeah. When we get to the white blood cells, when we get to the immune system, more you'll see some negative chemotaxis. Now, the cells that are actually directly capable of phagocytosis, neutrophils, eosinophils, monocytes. Remember that. So the neutrophils, the eosinophils, and the monocytes are directly capable of phagocytosis. They can gobble up whatever it is that is there. Now, on average, 5,000 white blood cells per microliter. What's the normal range that I gave you? I think I told you this, right? 5 to 10,000 would be in the normal range, 7,000 being the normal average. And when you get a differential, right, they're going to differentiate between these cells, and they're going to give you a percentage of these cells. There are 5 different types of white blood cells. They belong to 2 classes or groups. The first group are the granulocytes. This includes the neutrophils, the eosinophils, and the basophils. And those who are in lab recognize those percentages, right? Those are the same numbers you're going to see in lab. So you should have between, I think in lab I said 50 to 65. Here it says 50 to 70, okay? But around 50 to 70% of your white blood cells should be neutrophils. From the lab, that includes the segments and the bands. That's where the 70 comes from, okay? So the 50 to 65 was segmented, and the 0 to 5 was banded, so the maximum would be up to 70. Okay? And then the eosinophils between 2 and 4 and less than 1% would be the basophils. Then there are the agranulocytes. These are the cells without granular appearances in their cytoplasm. This includes the monocytes 2 to 8. I think in lab I said 3 to 8, okay? And lymphocytes 20 to 40. In the lab I said what? 25 to 33. So again, don't get too caught up on the exact numbers, but plus or minus a little bit is okay. Here are just a quick image of these cells. It would be incredibly rare to find all 5 of these white blood cells in the same little field of view, because white blood cells are already relatively rare compared to red blood cells, and to have one of everything in the same field of view under your microscope would be extremely rare. So here what we're seeing are all 5 types of these cells. And I'm going to go through the identification of these in lab. I'm going to skip over that for now. So the granular cells are the neutrophils, the eosinophils, and the basophils. And what you'll see in lab is that the neutrophils are rather neutral in color, that the eosinophils pick up this dye called eosin, and they're very bright red, and the basophils pick up a basic dye that causes them to be bluish or black in color. The monocytes are very, very monstrous in size, and the lymphocytes are cells, they're the smallest of the leukocytes, and they have a very large, round nucleus that takes up the majority of the cytoplasm. So we'll have a way of differentiating each of these cells when we get to lab. So I'm not going to go through this table with you. This will all be a good place for you to look over these details, and this will all connect with lab perfectly well. Now, what I want to do now is get to hemostasis. Hemostasis is basically blood clotting. That's what it means, blood halt. And this is going to happen when there's damage to your blood vessels. Any damage to your blood vessels is going to establish or initiate hemostasis. 3 phases to hemostasis. Number 1, vascular phase. I'll go through each of these. There's the vascular phase, then the platelet phase, and then finally the coagulation phase. Okay. So let's go through these. In the vascular phase, this is going to be the first 30 minutes or so after an injury. At this point, the endothelial cells, what are those cells? Endothelial. Endothelial cells are the simple squamous epithelium that lines the inside of all of your blood vessels. Okay? So endothelium, keyword, just a keyword for that simple squamous epithelium. And it's going to contract. Now, as that simple squamous epithelium contracts, it's going to leave gaps, isn't it, between the endothelial cells. And this is going to now expose some of the underlying basement membrane. Remember that epithelial cells are always sitting on a basement membrane. So we've got now exposed basement membrane. Those endothelial cells are also, in response to this injury, going to begin to release chemicals. Those chemicals are, one of them is endothelin. Endothelin. Okay? And basically what this is going to do is stimulate smooth muscle spasms. Remember what else is around your blood vessels? You've also got some smooth muscle, right? So by exposing these endothelial cells and the endothelin is released, it's going to cause smooth muscle spasm. So you got this kind of spazzing of the smooth muscle. And this is also going to start causing an acceleration of repair. So we're going to have some endothelial cells, some smooth muscle cells, and some fibroblasts. Even this endothelium is going to start the repair process. So immediately as soon as you cut yourself, right, we've already started the processes to initiate the repair of those cell types. That endothelial plasma membrane is going to become sticky. Okay, normally you want your endothelium to be very smooth because you want your blood cells to just kind of squeeze right through and have nothing sticking on the inside. But the endothelium becomes sticky, and this is going to start helping to seal off the tear. The small sides of capillaries will actually start to stick to each other, and this will start to slow down the blood flow and prevent flow. Okay. This is also going to be helping to have the platelets attach. You want your platelets also to just slide right through all of your capillaries normally, but when there's damage, they become sticky and the platelets start to stick to the inside of the vessel. Okay, so just looking at the picture, little knife blade, we've damaged the vessel. So now the smooth muscle is going to spasm. When you look at it this way, what does it make you appreciate? The spasm is going to do what? Restrict the blood flow. Right? So the spasm is going to actually really more, when I think of spasm, I think more of a shaking, but it truly does kind of squeeze it down and constricts the blood flow. It's going to reduce the blood flow, reduce the blood loss, and the endothelium is becoming sticky all at the same time. Then we go into the platelet phase. And now those platelets are beginning to stick to the endothelial surfaces, sticking to the basement membrane. The basement membrane also has a lot of collagen in it, and when you damage it, the collagen is now kind of sticking out into the vessel. So those exposed collagen fibers also begin to trigger things. Platelets are, as they get stuck, are going to start releasing certain molecules. The platelets are going to start releasing ADP. Now, ADP is like ATP, right? Except rather than adenosine triphosphate, it's adenosine diphosphate. And that actually stimulates more platelet aggregation. So ADP, right, stimulates the aggregation of platelets. You're going to have more chemicals released that further the vascular spasm. You're going to start releasing PDGF, platelet-derived growth factor, and this is also going to promote vessel repair. And finally, you're going to release calcium. Okay, I've told you over and over that calcium is important for blood clotting. So platelets have a fair amount of calcium within them. Upon damage, they release that calcium, and that calcium is now going to help also with the clotting process. So just taking a look at the cartoon, there's been damage. The endothelial cells are now exposing the smooth muscle and the basement membrane underneath it. And now the platelets are going to start sticking, and they're going to start releasing ADP, PDGF, calcium, these other factors to increase the vascular blood clotting. And then after we've gone through the platelet phase, now we go to the coagulation phase. And this is going to be after damage. And this is now when you start getting fibrin formed. So coagulation, or the blood clotting process, is going to involve fibrin. Now, where did that fibrin come from, folks? Fibrinogen. It was already there, right? It was already in the plasma. About 4% of your plasma proteins is fibrinogen. And it forms this insoluble fibrin. Now, there's a number of clotting factors that are necessary for this whole process to occur. It requires calcium, as it mentions, as well as 11 different proteins. So this is not there's what we call a cascade. There's a number of molecules that are necessary for this to occur. Most of them are proenzymes, which means that they are inactive. They're already there, but they're not active, right? If they were already active, then your blood would be constantly clotting. We don't want your blood to be constantly clotting. So these are pro-hormones, pre-active hormones, and they become activated through this cascade process. Now, there's two pathways that lead or are part of this coagulation phase. One is the extrinsic pathway. Now, these two things are not completely separate. They do work together. But the extrinsic pathway, what do you think? Extrinsic versus intrinsic. So what does extrinsic mean to you? From outside, right? An extrinsic pathway begins with the release of factor 3. Now, these numbers were named in the order of their discovery, not in the order of their use in the cascade. Sometimes I wish that scientists would just say, stop the madness, erase history, and let's rewrite this in a way that makes sense, shall we? Let's start with factor 1 and go through to factor 10. But oh no, we're going to start with factor 3. Okay, factor 3, that's the tissue factor, that's clotting factor 3. And that is going to be released by these damaged endothelial cells. The greater the damage, the greater amount of this factor 3 that will be released. Factor 3 combines with calcium to make and activate factor 10. Okay, so, right, 3 goes to 10. So 3 and calcium make activation of 10. Now 10 will be the first step in the common pathway. So let me just kind of show this to you. This is the extrinsic. Then there's the intrinsic. And this would be activated by collagen fibers at the injury site. And this pathway is going to get started with PF3. This is a factor that's going to released by the aggregating platelets. And this is also going to lead to factor 10. So what you see is that you've got two ways of leading to factor 10. That's all you want to think about. Extrinsic and intrinsic both set up 10. 10 is the beginning of the common pathway. From the common pathway, what I want you to know are these key words. I want you to know thrombin. So, factor 10 converts prothrombin into thrombin. Thrombin is the molecule that converts fibrinogen into fibrin. Okay, so we got to keep those terms straight. So factor 10 activates prothrombin. Prothrombin is the proenzyme, the pre-active form of thrombin. Thrombin then forms or cuts fibrinogen into fibrin. Now, after you have got the fibrin, or you got a clot, you've got the fibrous fibrin catching of all the cells, at some point, the clot's going to retract, right? You don't want this thing to stay there forever. So after you form this, it's going to tighten up, and it's going to continue to tighten up. But then at some point, you want to get rid of your blood clot, right? You don't want it to stay there forever. So we'll see that how the body comes along and cleans up the blood clot. Let's take a look at this picture. Again, there's been damage. You got the intrinsic versus the intrinsic pathway. But what's important is that they both lead into the common pathway. What I really want you to know is that. So we start off with factor 10 in the common pathway. That was the activation and the formation of thrombin. Thrombin is what made fibrin become fibrinogen. And that's the big one. Okay. What you see is that with tissue damage, we release factor 3. Factor 3 with calcium then goes on again to factor 10. Over here we had that clotting factors again, PF3, again activating 10. So this is showing everything in one picture. Again, I wish they would just kind of stop the madness and rewrite these clotting factors in the order in which they're involved. Once you have the clot, then we stop the bleed, but we want to start repairing that tissue. So then you go into fibrinolysis. Fibrinolysis is lysis of the what? Fibrin. What? We want to break down the clot factors. And so this is done by plasmin. So plasminogen is activated to plasmin. Now that sort of sounds a lot like the same thing of fibrinogen becoming fibrin. It's the same idea. These terms that end in ogen are the pre-molecules. They're the inactive molecules. So fibrinogen becomes fibrin, plasminogen becomes plasmin, and that happened by thrombin. Okay? And there's also this TPA molecule. You heard about TPA? The person goes into the hospital and we're suspecting a stroke, right? And there's a blood clot going to the brain. Well, what do we want to do? We want to restore that blood flow as quickly as possible, right? And so we want to give them, sometimes we'll give them TPA. And what that will do is hopefully go in there and give them a boost to open up that clot. We want to do that rather quickly. The faster you do it, the better the outcome, the better the restoration of function. The problem is, right, sometimes it can open the bleed up more and create more damage. So it's it's a little bit of a risk, but more often than not, it seems that TPA is something that's a good thing to do. Okay, so the last little bit is just a little bit about blood disorders, and I'll let you look through that. A little thing about sickle cell anemia, hemophilia, and thalassemias. And I think that finishes a unit, yes? Or was there platelets? That was it, right? Okay, so I'm going to say I'm done with blood. Look through the last couple of clinical vignettes. And other than that, we'll be done with blood. And we'll pick up with muscle on Thursday. For those who are going to lab exam, I'll give you a few extra minutes. Let's say 6:45. Okay, so a half hour to look over some things.